Okay, so let's have a look at this week's exercise and then a couple maybe little Python tips that might be useful for the exercise. If you want, you can open up Jupyter notebooks just to be able to play around and follow the example here. It's not totally necessary, and I don't have a kind of pre-made notebook for you to use, but it's simple enough, I think, to kind of type in some of the things that if you want to do that while we start going over the exercise, then when we get there, you can be ready for that part. But yeah, exercise number 5, of course, as already mentioned, is about the viscous flow of ice. And if we have a look at the notebook for this week's exercise, there's a few things to note. There's 3 problems, but only problems 1 and 2 are going to be graded. So the third one is optional. It kind of ends up being a lot of work if you do all 3 problems. So it's up to you. If you want to do it, of course, that's great, but it's not going to count for points in this case. So the first problem is about ice flowing in an open channel. This is the kind of velocity you would calculate for ice if you were looking down from map view, looking how it's flowing between 2 valley walls. And as usual, you first copy in your intro QG functions from the previous week, so you have something to work from. And then the first part is to take a look at the background and theory, just as a reminder for this first exercise, because we're going to start using this velocity equation. And if you want to understand a little bit of where that equation comes from, you can do that in the background and theory part of the course page. But the notable things here is that you can see we have a pressure gradient term like we've had in some of the other relations. We've got these power law exponents n in here that are material properties. And then we have things like h, which is the thickness of the ice, or in this case, the width of the glacier. And then y, which is the, in this case, distance from the center of the ice flow, which is why, again, it's maybe useful to look at things like this diagram, because it shows you, for instance, that we are assuming y is at the middle of the ice flow and that there's a range of values of y from plus h over 2 to minus h over 2, where h is the total thickness of the ice, or sorry, width of the ice. So you're given, I think, enough information here about what terms to use in the equation. You're given, for example, when dealing with this, a maximum ice flow velocity of 2.41 times 10 to the minus 6 meters per second at y equals 0. And then you're given some constants like a and h that you can use here. Your first task is to make a pressure gradient function. And in essence, what this is a function that will solve for this term here in the middle, the pressure gradient, because we don't know that. That's something that we can back out from things we can observe, but the pressure gradient itself is not so easy to measure. So we're calculating then what is this pressure gradient term. And you can assume that this whole thing is what you're calculating. So you don't need to calculate P1 and P2 and L and N separately, but instead you're going to just rearrange this equation with the assumption that you know what the velocity is at y equals 0 to be able to solve for this term P1 minus P0 over L raised to the power n. So you're just solving for that thing by rearranging the equation here. Your function should have a few different parameters that you're specified. So exponent, width, viscosity constant, and velocity max. And then there's some tests here to check and see if your function is working properly. So that's step number 1 in the problem, is essentially a little bit of algebra and making a sort of Python function that then solves for what that pressure gradient term would be if we know what the velocity is at y equals 0. After that, we can then go on to calculating the flow velocity by making another function. Because we have this thing to calculate what the channel pressure is, we can then take advantage of that function to be able to use, where's our equation here, this equation to come up with what the velocity is as a function of different values of y from one valley wall to the other, we can calculate the velocity, because we can come up with this term from our pressure function that you create in the previous part, and all these other things are knowable in terms of what's given to you. So you make another function for calculating what the channel velocity is, and then again there's some tests for that one. Then you're given some numbers where you can calculate, if you assume the width of the channel is a certain, like in this case it's 1400 meters, you can calculate for different power law exponents what the velocity of the fluid would be flowing down, or what the ice velocity is flowing down this valley. And then you're told to store this in a pandas data frame. Again, here the hints for this week's exercise might be helpful, so have a look on the course page if you get stuck. At least for, I think for testing your pressure function, I think I have examples of what value you should get for the 4 different power law exponents we use, so you can check to make sure that you're getting the right values with that. So you're going to calculate ice flow velocities, and I bet you can guess what's coming after that. It's plotting your results. So no surprise. Once you've done the calculations, you make a plot that shows then what the velocities look like. And that's it for the first problem. Kind of going through from start to finish there. For problem number 2, we're going to then compare to observed ice velocities from the Saskatchewan Glacier in this is in the Canadian Rocky Mountains, and we're basically going to be reading in some velocity data from a data file. So here you've got distance from the center of the glacier, and then the velocity in meters per year and meters per second for those two, or for each of the points where there is a velocity that's been recorded. So you're going to read the data file in, that's their first step, and then you're going to calculate the velocity for these different power law exponents and compare your prediction to the measured values of the velocity from the data file. And you're going to use this, or do this, by using the chi-squared function from back in exercise number 2. Because essentially what we can do is at each point we can say, okay, if I'm this far from the center of the ice, what's the velocity my model says, what's the velocities observed, subtract the two from each other, and raise, square that. You basically can just use your chi-squared function, and you should get then a kind of goodness of fit in the end that shows how well each of the different power law exponents fit the measured velocities. In order to do this, we're assuming that we have standard deviation for the observed velocities of 2 meters per year. That's totally just an arbitrary thing in this case, but in order to use the chi-squared function, you have to have not only the measured ice velocity and the predicted ice velocity, but also an uncertainty. And so in this case, we'll just assume 2 meters per year as the standard deviation for the ice velocity. So you'll go through and do that. And again, after that, once you have your different goodness of fit values, you'll make another plot here where you plot your predicted velocities for the ice flow, and you plot the points that are the measured values for the ice flow, and add the goodness of fit value for the best one to the plot to sort of show which power law exponent gives the best fit to the measured velocity data. So this is basically a lot of the, applying what's done in problem number 1. That's in essence what it is. And then finally, the ice flowing down an inclined plane. This is problem 3, which again is optional. And here we're using another glacier from the Canadian Rockies, just because that's where the data I found were from. And again, for this, there's the background and theory section you should have a look at first, because now we're looking at a kind of cross-section view of the ice rather than the map view we had before, and we have a different velocity profile as a result. So you're given this then, and like before, we have this weird term in here. In this case, it's gamma x to the power n. So this gamma x term is an unknown gravitational force term and it's the downslope component of the gravitational force, which is something we can make a function to be able to calculate if we know what the velocity is, for instance, at the top of the ice and at the base and blah, blah, blah. We can solve then to find what this gamma x to the n term is, like what you did in problem number 1 for this pressure gradient term. So you make a function to do that, and after that then you do just like you did before, where you then can use that function to calculate what the ice flow velocity is by making another function for that. Read in a data file with some observed ice flow velocities and compare your predictions to the results of your model, once again, to figure out which power law exponent gives the best fit to your data when you look now in profile rather than in map view. And finally, plot your results to be able to visualize what you've done. And at the very end, there's a couple reflection questions if you want to then think a little bit more about what the exercise was about and answer those. That's, of course, always welcome. But yeah, that's the kind of overview for exercise number 5. Do you have any questions about the exercise at this point? All right, so if not, there are a couple things I was going to show you here that I just put into a Jupyter notebook that are things you're going to need to know for this week's exercise. So one of them is about how to determine whether a number is odd or even in Python, because what you're going to see is there's one equation that gets a little bit funny for negative values of, in this case, I can't remember if it's y or z. I guess it's y that's used. If you get negative values of y, you get a weird velocity. And it only happens when the power law exponent that you're using is even. So you have to be able to figure out how do we know whether a number is odd or even in Python. And so there is a mathematical operator we haven't seen before, at least I don't think we've seen in any course that I've taught Python in, called the modulo operator, which basically is like doing long division with integer numbers, and it gives you the remainder after doing the division. So if something divides evenly into the number, like if you took 4 and then divided by 2, you would have a remainder of 0, because 2 goes evenly into 4. And if you, of course, took 5 and divided by 2, you would have a remainder of 1, because you could get 4 of the 5 in there by doing 2 times 2, but then you have 1 left over. In Python, we could basically do this with the percent sign. If you do 4% 2 and run this, you get back a number of 0, which is the remainder from doing that division. If we did 5% 2, you get back a remainder of 1, which indicates that not only do we have a remainder, but the 2 doesn't go into that evenly, which means this is not an even number. And that's essentially the trick for figuring out if a number is odd or even in Python, is if you can divide it, whatever the number is, and you get a remainder of 0 doing this, you know it's an even number. If you don't get a remainder, then yeah, you have an even number. If you do, you must have an odd number. So it doesn't matter how big this number is. Of course, it ends in 4, so we know this is an even number. This is basically the trick to doing this. And because this modulo always gives you back just the remainder, you don't know how many times this goes in here, but you know that you have something left over. With this in mind, then what you can do is, like, let's say we have some number that let's just arbitrarily call number. And we'll just say number equals 9. You can basically say if number %2 is equal to 0, then we can print. Let's make an F string for this. Let's make this be number is even. I'll just delete the other one here. So we know if it goes and there's no remainder when you divide by 2, then it must be even. Otherwise, we can say print that number is odd. And I need to do it like that. So like this, I must have, there we go. Like that, we can see that 9 is odd. And if I change this to 8, we get 8 is even. It's a simple trick, but that's the fastest way to figure out if a number is odd or even, as far as I know. In Python, is just to do this remainder type division and see what if the remainder is 0. Of course, if you divide by something other than 2, that doesn't work, but it works for dividing by 2. So you're going to need this because, like I said, you're going to get some weird velocities for one of the equations when you have values of y that are negative and certain power law exponents. I can put this notebook on the course page as well, so if you want to have this, I'll post that. But another thing we can do is if we want to look at an example of how this works, I can import NumPy and Matplotlib like usual here. And this is not the equation that we'll use for the velocity calculation that's done in the exercise, but it's a similar one. And so if we define some range of x values using the linspace function to go from 0 to 1 and whatever, it doesn't matter if you have 51 or 10 steps or whatever here, but we calculate, some range of x values. Let me put this into two separate. Let's do it like this. So import this, and I'm going to move this to another cell. So we define some range of x values like this from 0 to 1 in 51 steps. So we can see our x array looks like that, going from 0 to 1 in steps of 0.02. We could then have some velocity equation, which I guess maybe I'll make a simple example here first as our fake velocity equation. That says our value of y is equal to 1 minus x to the power n plus 1. And so then we can give a power law exponent, for instance, n equals 1. And if our velocity looks like this, we could then do plt dot plot x comma y. So we define this range of x values from 0 to 1. We make some fake velocity function here that we're going to call y, but we could call that u if you wanted to instead, which would be more like an x component of a velocity. But here it's just 1 minus x to the power n plus 1. And then we plot that. So the expectation here would be that you'd have some kind of upside down parabola because you're going to have n, so x squared, 1 minus x squared gives us something that looks like the right half of an upside down parabolic function. That's fine. And if we changed our n value to be n squared and ran this again, you get slightly different shape, a little bit kind of steeper rolling over in the curve. And of course, if you keep going up to n equals 4, you get more like it's flat and then kind of curves over more quickly, whatever. This is all fine. So if we took this and took the same basic idea, which is what I kind of have done here. So for n in range 1 to 6, so this is basically going to go actually from 1, 2, 3, 4, and 5. Here's the y value, same function we were just using, and then plot this x comma y, and then just add in a label here to say what the exponent is. This is going to plot then 5 different, 5 different lines that look like this. So this is kind of like the right half of our velocity profile. In this case, looking down in map view so kind of looking down from above, here's the valley wall on this side where the velocity goes to 0. So you can see that's what happens at this point. Here's the middle of the ice flow. That's more or less what we're looking at in this kind of view. Looking down from above, so our velocity goes to a maximum of 1, and this is a simplified version of what you have to do in the exercise. This is all fine, no problems here. If we change things so that our values of x, and maybe I'll just do it here, that I'll make another cell and say x equals np.linspace minus 1 to 1.0. So instead of going from 0 to 1, let's go from minus 1 to 1 in 51 steps. And run the same thing we just did. Here we get some weirdness, because we're expecting this to kind of be a symmetric solution, that our velocity should obey this boundary condition over here, that it has to go to 0 at this other channel wall, which would be like the kind of other side of our flow, but it doesn't. It flips up like this. It's like, I don't know, if you have one of those bad days where your hair just wants to kind of like not go down. It's flipping up and it won't sort of behave properly. And in order to handle this, we need to kind of use some trick. And our trick is to identify the cases where this thing doesn't work very well. And what you can see is that here, the red one and the orange one are the ones that cause trouble. And they cause trouble when the value of x is less than 1. Or sorry, less than 0. So what you can see, of course, here is that here is why it's good to be able to figure out whether we have an odd or an even number, is because we have an even exponent and an even exponent here that are the ones causing trouble. So we know to fix this, we have to be able to figure out that we have x less than 0 and an even exponent. And in that case, we need to use a slightly different equation to handle those examples. So let's put that in here. So if we imagine that we calculate first our velocity, assuming everything is good, we have y equals 1 minus x to the power n plus 1. That's fine. But let's put in a little test here that says if our value of x is less than 0, and our exponent is an even number, which means that when we divide it by 2, we get a remainder of 0. So this is basically our even number test, and this is checking for the values of x that are less than 0. In order for this to work properly, we would need to actually loop over all the values of x and check each one every time we calculate the velocity. So this might seem like an intuitive way to do things, but it's kind of not that nice because we have to loop over the x values to get this to work. There's a better way to do this. Let's get rid of that part of the test and say we only check to see if our exponent is even. If our exponent is even, what we're going to do is we'll say that y, and then we can use this array selection in Python, or in NumPy rather. So the y values where x is less than 0, we're going to use a different equation. And for this, we're going to say instead of 1 minus the x squared term, which is what causes this kind of flip up thing over here, we're going to say it's 1 plus x to the n plus 1. The thing is here, we have to also say that we're only using the values of x where x is less than 0. So this, if you haven't seen it before, I don't think we would have introduced it elsewhere in the course, but this kind of construct like this, where you take a NumPy array and then you give within here some kind of range of values that would be kind of a true or false type thing. Values of this y where x is less than 0 will be true, if the value of x at that corresponding position is less than 0, or false if it's greater than 0. So this will only then modify the values of y where this condition applies. We can do this in several ways, but this is the kind of NumPy-like approach to doing this, which is basically just to give this condition in here. Just to show you what this does, I'll just add a cell here. If we just took the x less than 0 and ran that, what you get back is an array of true and false values. So every place where x is less than 0, it's true, and every place where that's not true, it's false. So what this is going to do is it's going to select values out of y on the basis of this condition x is less than 0, using the trues and falses here, and it's only going to modify the values where this condition is true. So this is the NumPy-like array approach of dealing with this kind of problem. Rather than having a for loop that goes to each x value and checks what's your, are you negative or not, and then calculates the velocity for that one, you do it all at once as an array operation, which is far more efficient, especially if arrays get bigger. Like this can, this takes sort of milliseconds at most to do this, even for fairly big arrays. Whereas if you do it with a for loop, it's pretty slow. The key thing here is that we have to have this value of x that's used in the equation also have that same condition. Otherwise, if we pass in the entire equation, the entire array of x values, what you end up with here is you have maybe, I don't know, half, so like 26 or 25 of the values in this equation where you're trying to calculate y, and then all 51 values for x, and you'll get some error message that basically says you can't put 51 values into 25 spots, which it may or may not be clear what that message means. But so you have to still have this selection in here to be able to work with this. But if you do that, we have basically two steps. So we have find whether we have an even number, and then use a different equation if the values of x are negative. Those are our two tests. And if we run this now, we solve the problem of the little flip up hairs that don't want to be nice. Because you'll see you only modify things on the left side of the plot, and only for those exponents where the exponent value is even. So yeah, those are the two kind of Python things you need for this week. They're not necessarily like, I guess the even numbers thing is a Python thing. The other part is maybe something about, well, I guess we haven't seen this NumPy kind of selection based on these conditions like what was shown here. So I guess that's useful to know that as well. But mostly, that's a place where every year there's a lot of questions about this, because it's just a problem with the equation that's used. That it works very nicely as long as you go from 0 to positive values, but as soon as you want to put things negative to have a nice symmetric picture of the whole glacier, it doesn't work. And the thing is that we have velocities that are in this data table. For instance, here, if we scroll back to the data that's used in problem number 2, you'll see the velocities are from the center both to minus and positive sides of the middle of the ice. So to plot things nicely, it's good to be able to get the velocities to work nicely on both sides of the center line at y equals 0. Any questions about that stuff? Did this kind of array selection thing make sense with the NumPy arrays? Or, yeah. I mean, you can do lots of different things with this, like this kind of slicing or whatever you consider it here. This kind of putting a condition in there, you can do a lot of things. You could, for example, I think I can delete this one because there's nothing in there that's not above. If we said, let's say, exponents equals np dot lin space, and let's make it go from 1 to 100 in, actually let's not use lin space, let's use what's the other one? A range. Let's go from 1 to 100 in steps of 1. So if we just print out what exponents is, we have this NumPy array that goes from 1 to 99 in steps of 1. These are integer values here. We could say exponents where the condition is exponents %2 equals 0. So we could take the values in the array, and wherever it's true that we can get division by 2 gives no remainder, we could get that subset this way. So this is only the even values out of this array. So you can do lots of different things. I mean, you can do less than, greater than, exactly equal to a certain value, all kinds of different tests like that. But extracting these slices is really quick. Extracting the kind of subsets of the values this way is fast. And again, it comes back to the idea that if we took our array and we just said the values of it that are dividing by 2 evenly, we get false, true, false, true, false, true. Of course, since numbers go even, odd, at least with real numbers, then you get back this kind of every other number is odd and every other number is even. So this is the true and false array that comes from that, and then that's what's used to then select the values out of our starting array. So yeah, that's maybe everything you need to know as far as exercise 5 goes. I haven't introduced this stuff in the past, but I've just gotten kind of, I don't know if it's annoying to the students that you have to encounter this and then get stuck trying to figure out what to do, because it's like not knowing how to figure out if a number is even and not knowing how to modify the equations. It will still cause you a little bit of trouble, I'm guessing, because you're going to deal with a little bit more complicated equation than this one, but it's not that different. In essence, it is pretty much this with some other scalar terms in there, so it's not too terribly different.
Are you going to share this on the website?
Yeah, I'll put this one to the webpage.
At least the modifying of the NumPy array. Quite handy.
Yeah. Yeah, I used to introduce a lot more stuff about NumPy earlier, but that's back when I used to do everything like reading data files with NumPy and all of that stuff, and it's actually far easier to do some of that stuff with pandas. So yeah. Now I introduce a lot less NumPy. But yeah, I could put this to the web page.
I remember I did this course in 2019, and that was actually at that time we used a lot of NumPy.
Yeah.
Then I realized also that pandas is quite flexible.
Yeah, that's right. That's right. Yeah, there was even, I think, one odd year where we did the GeoPython course where there were 2 like groups that split. So yeah, half of them did pandas, half of them did NumPy. Yeah. And then it became very clear that was a terrible way to organize the course. Yeah. So that was the end of that experiment. It was such a headache to grade everything because you had to know, anyway, that was a mess. But yeah, I'll put this one on the course page someplace. Maybe I'll stick this with the hints for exercise 5. I'll just kind of put a link to the notebook there. Or, well, I don't know. I'll make it somehow findable in the lesson 5 materials. So you'll have this. Yeah, any other questions or anything like that? And yeah, I mean, so basically we're given 2 different boundary conditions that end up making a pretty significant difference in the temperatures you calculate. So in the first case, what we assume is that we have a constant surface temperature of 0. I think that's the case for both of them. But a constant thermal gradient at the surface, which means the slope of the geotherm is fixed at the surface. And in order for that to be the case, in essence, you get a different kind of behavior in terms of this steady state equation than you see for the transient case. So most likely, I'm guessing what you saw is that when you increase the velocity of advection, it actually changed the temperature at the bottom of the model to be colder than it was when you had a slower velocity. Is that right? So, like, I guess if there's nothing else, that's kind of it for us for today. So, yeah, as usual, Friday, Levy will be there and ready and willing to help if you have questions. And next week, we're going back to thermochronology. It'll be the first of a two-part exercise for the last 2 weeks of the course that also relates to the final project in the course. So if I'm sufficiently organized, we'll introduce the kind of idea for exercises 6 and 7, and also the final project idea next week, so you can see how the pieces all fit together for that. But I'll also, if you haven't put I think 8 people had filled in the midterm feedback. If you haven't put something there yet, please, you still have time to put something in the midterm feedback. And then I could also kind of share a summary of the midterm feedback. I didn't see anything that looked totally alarming at this point, so I didn't feel like there was an urgent need to take action. But if you have any comments, please put them into the midterm feedback.